Hi, I'm Pablo Barros, and today I will talk a little bit about my experience on affective perception from a computer scientist perspective, and the lessons I got when I was slammed in the face when trying to create applications of facial expression recognition that did not work. So, let me start by introducing myself. I am originally from Brazil, and that's the reason for the funny accent. And there, I did my bachelor's and master's study. In Hamburg, Germany, I completed my PhD. And in Hamburg, I started working on affective computing, in particular on the personalization of affective perception. And for 1 year now, I'm working at the Italian Institute of Technology in Genova, where I'm going in depth on the idea of affective perception, but now included in an action perception cycle, focusing on how we can generate and modulate behavior based on affective scene interpretation. I started working on affective computing from a computer science perspective. I was studying deep neural networks, and facial expression recognition was a popular task at the time. And then I decided to try things out. Well, it did not work. I went deeper and deeper until I realized I was into something new. The problems are not with the ConvNet that does not train, but I lack the understanding of affective perception. One of the first principles I got to learn and to explore is the idea that there exists a set of basic emotions which compose more complex concepts and are perceived by different persons. This was widely supported also from my computer science perspective. The datasets I used to train and evaluate my models usually refer to the basic emotions to justify labeling techniques and choice of emotional ranges. This, of course, leads to an understanding of a universality argument that persons from different cultural backgrounds can characterize and understand the set of basic emotions. Again, this reflects directly on how the datasets we use were composed and designed, and thus on how we build, evaluate, and to which scenarios we deploy our automatic perception models. The problem is that this was usually not enough to provide an universal emotion perception model. Deploying a model in a robot, for example, usually did not produce a good performance, or when used in a real-world scenario, like a demo, it did not achieve the 90 or 95% accuracy it had when evaluated in a dataset. Of course, we started looking into this from a model performance or a computer science perspective. Maybe we did not have enough data samples on the dataset, a variety of data and the labels are wrong, or the network is just not learning what it's supposed to learn. But only recently, the entire concept of universal emotions started to be seriously questioned. And recent works started to shed some light on how the experiments that Ekman did in the 70s maybe were interpreted differently than they should have been. The entire concept of emotions as something which is not a monotonic definition is very well spread. But its definition is a concept that is created by the individual, making the individual perception and understanding of affect a norm instead of the generalized universal concept is rather new. The impact these findings have on our computational models is huge, especially on its application and adaptation towards different scenarios. But why our models work when trained on, let's say, in the wild datasets or unconstrained scenarios? How can they depict patterns embedded in the labels and achieve a good performance? Well, in this regard, if we see each dataset we train and evaluate our models on as an individual word representation with its specific characteristics, whether on data distribution and processing, labeling schemes, and evaluation metrics, it kind of fits the argument of individualized affective concepts. When labeling such datasets, we usually apply some inductive bias by presenting already the boundaries of the labels. For example, choose one of 5 categories, or between positive and negative range. Even when this data is collected from an in the wild dataset, we apply the same preprocessing techniques to all the image. We try to balance the distribution of the labels based on the labels we already biased, and so on. So, if we see all these individual datasets as one word representation, each of them, it kind of makes sense that we can train and recognize facial expression recognition models on them quite well. But how can we make these models easily adaptable towards other word representations, other scenarios? In our investigations, we believe that the response is on the data itself. We are training and evaluating these models based on faces. Faces contain a limited amount of information. Eyes, mouth, nose position, cheeks are all structures which are easily perceivable and easily identifiable. They happen more or less in the same place, have very similar and distinct shapes, and when we are expressing emotions, the regions we change in our face are very restricted. Deep learning models have trained to highlight the similarities in specific regions of the data and use them to create decision boundaries, if we're talking about supervised learning, of course. A deep neural network trained on different datasets with different labels highlight the same facial structures. In a supervised task, this is extremely sensitive to the labels themselves. If the data has no distinction between smiles and frowning, this of course would not be learned. This is so strong that sending a non-facial image to a ConvNet, it will try to detect facial characteristics on them. And of course, this means these structures are the backbone of the universality of emotional expression recognition in these models. And we got to a point where we can use these representations and manipulate them. Recently, we proposed a generative adversarial network that can encode faces into an entangled representation. Using the same principle, we can decode this entangled representation and generate faces. To guarantee that the entangled faces carried affective information, we enforce the decoder to describe a face over an arousal valence value. Adding a condition of factors, we can have a control over how these faces are generated or edited in terms of arousal valence. We then use this facial representation that the encoder learns to create clusters of similar representations, of similar affective representations. When clustering the data from a single person, we can identify how this specific person expresses emotions. And because we can edit these faces with only one example of someone's face, the network could generate edited versions of this face within an entire scale of arousal valence. This way, this network could have the first idea of how this person should perform expression. Again, this is only valid if we assume that the understanding of an expression is given. It is normalized by the universe this network is presented into. In this case, the specific dataset this network was trained on. And this problem affects process of describing these clusters. If you imagine that these clusters are unique to that person, to understand these clusters, we have to understand that person in particular. We have to understand how this person expresses emotions, how this person reacts when presented by a situation, and how this person behaves when trying to express this emotion. For this specific work, we wanted to measure if the process that we presented improved emotion perception, and thus we give these clusters labels based on the data set we trained this network on. In this case, we specialize these individual clusters to specify this data set culture, this data set information as a word, as a unique word. Knowing that we can represent facial expressions so well, we are now trying to reach one step further, disentangling the understanding of these expressions from the facial perception characteristics itself. And our next step was to address the differences between generalization and personalization of affective perception. Where the generalization forms the norm of the universe we're dealing with, in this specific case, the whole data set, personalization tries to understand emotions from an individual's perspective. In this regard, we propose the affective memory framework. It is a modular neural network architecture that is composed of 4 components. The first of them is a manner of representing an expression, and of course, we use a convolutional neural network to learn this affective representation from audio and visual stimuli. We focus on pre-training this ConvNet in a supervised manner. It has as a goal to be able to represent affective features from face and audio. And because we wanted to integrate the audio channel here, using the unsupervised approach that we proposed before did not produce the robust representations we need on the audio channel. Our second component represents a general emotional clustering. Using the same principles of our previous work, we use a self-organizing network that creates clusters of similar affective representations coming from the first module. We train this network to cluster the entire dataset. So we can create a predefined and affective perception given by the word. In this case, a cultural perception bias coming from the dataset, but without relying on the label structure itself, but only on the data representation. Our third mechanism explores growing self-organizing networks to create individual affective clusters, similar to our previous work. Each network clusters information coming from one single person, meaning that each network can have different clusters from one single person. The difference here is that instead of labeling these clusters with a predefined label, they inherit the cluster labels from the generative representation. This means each cluster within the individual affective memory specializes the clusters of the general representations. So we can identify, using both networks, how different a perceived stimuli is from each other. Our fourth and last module realizes the integration of general and personalized representations. It is also a growing self-organizing network, but with the difference that this one is trained online. It merges both individual and general representations and creates a prototype neuron to mirror them. As this network grows and shrinks accordingly to what was perceived, it adds a dynamic component to the perceived stimuli. Neurons are created and are removed depending on what is being shown to the network. By reading all the neurons of the network at any time step, we are able to have a stateful representation of what was perceived so far. This module is the only one that receives a label from the dataset, from the cultural representation that the network is applied to. Meaning, we are able to map arousal and valence information from each prototype neuron and have a continuous affective reading from the entire network. This is the only part of the network that has contact with the external world. And this is where we bias the understanding of the model's representation in order to make it useful to this specific task. To evaluate this model in particular, we use the OMG-Emotion Dataset, which contains long videos with monologue performance. In each video, a single person performs an emotional scene for more than 1 minute, which allows us to track how that specific person is expressing a set of emotions over time. We evaluate our model in each individual video in order to identify if we are able to represent the very specific emotion dynamics that each person has. The most important behavior our model showed was the capability to provide a first impression performance, meaning that it could already from the beginning of the video, without any knowledge about that person, infer some predefined affective information. But over time, it learned how to distinguish that specific person's affective expression capability from the general norm, and improved the representation and recognition performance. This happened in both terms of arousal and valence, as both of these representations are pre-established and constrained to that specific dataset, and thus individual word representation. We cannot necessarily extrapolate them into other scenarios. Our model, however, can be easily adapted to other scenarios, as the bias towards the specific affective representation only happens at the end, after the network learns how to represent and cluster affect. So, to summarize the points I discussed here today, I do believe that we can provide affective perception on a more global scale, but for that, we should focus on understanding the differences between facial expression representation and affective categorization, especially if we have to focus on understanding the application, the use, and the specific scenarios we want to deploy these systems. Also, focusing on an individual affective understanding, whether truly individual, personal-wise, or scenario-wise, is extremely necessary. This way, we can start thinking about transfer learning, not only on a feature level, but maybe even on a contextual level. I do believe we are moving into this direction, but a lot is still missing. We still want to focus on self-adaptation and active exploration, which will allow us to get away from predefined and biased labeling understanding. And most importantly, we have to start seeing perception as something more than an individual classification. Concepts of shared perception, sense understanding, action and behavior generation, all of that impact how we express and understand emotions. And we should move into this direction to develop models that can be useful in different scenarios in the future. Well, and with that, I finished this presentation. I hope you enjoyed it as much as I did making it. I want to thank the workshop organizers for the opportunity of making this talk. It is a great conference and a great workshop concept, and I'm very happy to share with you all a little of what we're doing and the vision we have for our future research. If you want to discuss any of these topics as much and much more after the workshop, you can contact me over these links. Also, we have all the models presented here on our GitHub account listed here. Thank you all.